This is your paper EL1501 unit 4. Now we are starting CI2 examination point of view. This is our lecture number 1. Be careful, this is for CI2 examination. Our topic is floating point representation of number. Floating point representation of number. What is here? Okay. Here in the decimal number system, very large and very small numbers are expressed scientific notification. Okay. For example, the decimal number. See here, we all discuss in terms of with the help of examples. Here we are taking example of decimal number 51729.739. It is represented in scientific notification as plus 5.1729.739 into 10 raised to 4 plus 0 4. This is the scientific notation. Right? Why here 4? Because we are using 1, 2, 3, 4 after this point. So 1, 2, 3, 4, 1, 2, 3, 4. This is your point. So we are taking here 10 raised to 4. Here the word manitas, which is the first part, represents a sign, fixed point number called as manitas. This manitas, it is equal to plus 5.1729739 and exponent. What is exponent? So here exponent is the second part of the designates the position of the decimal point, and it is called as exponent. So here the exponent, it is equal to plus 4, or we can say plus 0 4. Here the manitas is considered to be a fixed point fraction. This representation is equivalent to the number expressed as a fraction 10 times by an exponent. This is your 10 times. Similarly, binary number can be expressed by the scientific notation known as the floating point representation of number. Floating point representation of number. This floating point representation of a number consists of two parts. It is divided into two parts. The first part represents a sign. The first part represents the sign, fixed point number and fixed point number. It is also known as manitas. Which is also known as manitas. The second part designates the position of the binary point, and it is called the exponent. The second part is the position, which is known as exponent. It is denoted by E, exponent E. The fixed point manitas may be a fraction or an integer part of the number. So this is maybe a fraction number or integer number. Here S, the floating point number represented in binary by the expression. So this floating point number in terms of expression of the floating point number is -1 raised to s. S means sign, into significant into 2 raised to exponent plus bias Here S is the sign bit defined as, this S is the sign bit. It is defined as 0 for positive number and 1 for negative number. Right? So you just follow this chart. All of this very easy to remember. Significant defines the magnitude of manitas and bias is the value. Significant is the manitas, significant defines the magnitude of manitas. Magnitude, the meaning of the magnitude is value, or we can say magnitude of manitas. While the bias is the value that is used to control the range of the number. This bias is the value which control the range of the number. The range of the number. Okay. So here there are two floating point standard which is called as single precision and double precision. Again, this floating point, there is a 2 points, single precision and second point is the double precision. Now, what is inside the single precision? So we will see here with the help of chart. We can see this is the format of single precision floating point number. This is the format. This S, this is your D31. The second one is the bias exponent. Bias exponent D30. D30 to D23. And then the significant. Here D22 to D0 number bits. This is the format of figure, is the format of single precision floating point number. What is this? So in this single precision, the word size of the floating point number is 32 bits. Here the word size, it is equal to 32 bit. What is this? We can discuss when we are taking the example. 32 bits. And 127 is the bias. 127 bias 127. The format of single precision floating point number is shown in the figure. Out of these 32 bits, total 32 bits, MSB, that means this one, MSB shows sign. That means D31 shows the sign. LSB 23 bits, these 23 bits, D22 to D0 are used for significant. Then the remaining D30 to D23, this D30 to D23, this 8 bit, this total 8 bits, this is used for the bias exponent. This is used for the bias exponent. So now we are taking the example. So it is very clear for you to understand. Right? Let us consider the example of decimal number 44.25. Decimal number 44.25 decimal. Its binary representation, it is equal to, so first of all convert this decimal number into the form of binary. So we direct write down binary number is 101100.01. This is the binary number of 44.25 decimal number. Right? Now convert this into Manitas 1.01100001. 1, 2, 3, 4, 5. Right? So into 2 raised to 5. The Manitas is converted to 23 bits. This Manitas is converted into 23 bits. So significant value 23 bits significant value by putting 0 to the right side of the number. So significant, this significant it is equal to this 101100001, 101100001, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 and 23. So remaining are 0. 0 to the right side of the number. This is your significant. The bias exponent is the sum of the bias exponent is the sum of exponent value. Here the exponent value is 5. This is your exponent. So we write down here, and the bias. So for single precision floating point, this is your 127. Be remember. For single 127 and for double 256. For double 256. For single the bias is maximum 127. So it is given as bias exponent, it is equal to 5 plus 127, that is equal to 132 in terms of decimal. So convert this into the form of binary. So bias exponent, it is equal to 132 decimal conversion of binary, it is equal to 1000100. So the number is positive, hence the sign bit is 0, and the single precision floating point representation of the given number is, so in terms of this we can write the first one is the sign, the number is positive, so we write down 0. The second one is bias exponent. What is your bias exponent? This is your bias exponent, the total bit 1, 2, 3, 4, 5, 6, 7, 8. So here for single precision 8 bit bias exponent, right? So bias exponent is it is equal to 100000100. And the last one is the significant. This is our significant. This total number is 32 bit. So write down 101100001 1 2 3 4 5 6 7 8 9 10 11 12 30 40 50 60 17 18 19 20 21 22 and 23. So in this way total number of bits, it is equal to 1 2 3 4 5 6 7 8 9 10 11 12 30 40 50 60 70 80 90 20 21 22 23 24 25 26 27 28 29 30 31 and 32. So total bits it is equal to 32, which is known as word size. This is your sign, this is your bias exponent, 8 bit, and this is your significant, and this is your total 23 bits. Very simple. Same thing we are discussing for double precision. So in double precision, the word size it is equal to 64 bits. Again, draw the format. Same thing. First one is the sign. Position is D63. Second one is the bias exponent. D62 to D52. And the last one is the significant. This is your D51 to D0. So D0 to D51 significant, D52 to D62 bias exponent, and D63 shows the sign. Right? So let us consider example. Here we are taking the direct example. Example is 1144.125. This decimal number. Consider the example of decimal number 144.125. Its binary representation, it is equal to 1000.001. So its significant is equal to 1.0010000 last 001. 1 2 3 4 5 6 7, so into 2 raised to 7, right? The many task is converted to 52 bits. This many task is converted into 52 bits. Be remember, in single precision, the many task is converted how many? 23 bits. Here the many task is converted into 52 bits. So the value by putting 0 to the right hand side. So the significant it is equal to 1001 0000 001, and the remaining are 1 2 3 4 5 6 7 8 9 10 11 12 30 40 50 60 70 80 90 20 21 22 23 24 25 26 27 28 29 30 31 32 33 34 35 36 37 38 39 40 41 42 43 44 45 46 47 48 49 50 51 and 52. So total bit from here to here, total bits is equal to 52. Now we want to find out, this is your significant. Now we want to find out exponent, bias exponent. The bias exponent is the bias exponent is the sum of exponent value 7 this and bias 256. Be remember in the single precision floating point number there are not 256, there is 127. Here 256 because this is your double precision floating. So total bias exponent it is equal to 5 plus 256, it is equal to 261 decimal. Using the conversion technique, its 11 bits binary representation is this is your 11 bit. So the bias exponent it is equal to converting this into the 11 bit, convert this decimal number into 11 bits binary number, and it is equal to 00100000111 1 2 3 4 5 6 7 8 9 10 and 11. So the number is negative, this number is negative. So whatever we are putting here sign, the sign bit is, it is equal to 1, and the double precision floating point representation of the given number is this. First of all sign, so we are using 1 because the number is negative. Then the bias exponent, this is your bias exponent, write down this 0 0 1 0 0 0 0 0 1 1 1, right? And the last one is the significant, and this is your significant. So 1 0 0 1 0 0 0 0 0 0 1, and then 0 0 0 0 up to 52 bits, right? So the total number of bits, how many? Total number of bits 64. This is your 52 bits. This is your bias exponent is your 1 2 3 4 5 6 7 8 9 10 and 11 bits, and this is your 152 plus 11 plus 1, that means 64. And this is nothing but it is your word. This is your word, total number of bits, word size. So in this way, up to this you practice. Next time we are discussing about the binary arithmetic. Thank you.